Okay, welcome back. We're going to look at problem 0.46. This is again from our introduction to discrete mathematics. So we're asked to show that there is an injection from A to B if and only if there's a surjection from B to A. Believe it or not, I think this one it might sort of be beyond the scope, maybe not even of just this chapter, I think certainly of this chapter, but maybe in this book. What we're going to find is that to actually give a real general proof of this, we're going to need to rely on something called the Axiom of Choice. Now, as I've mentioned, I don't sit down and really read through all the sections necessarily, but I do sort of scan through them, and I did see that they do mention this. They do mention the equivalence, the logical equivalence between Zorn's lemma and the Axiom of Choice, but they never actually tell you what the Axiom of Choice is, how it works, anything like that. And it actually is necessary for this. I imagine, my guess here is that the author sort of intended for the student to sort of approach this problem at whatever level of sort of wherever their intuition was sort of operating at, which I think, like, for example, if this is maybe your first course in sort of proof-based mathematics, you might have approached this a different way than we're going to approach it, and that's fine. I think that's kind of what the author intended, to just kind of leave it up to the student to, try to get this problem however it seemed to fit within the way they understood the content. For us, we want to try to prove it in as general a case as possible. So to do that, we're going to need the Axiom of Choice, which again wasn't actually stated in the chapter. I haven't read the rest of the chapters. I probably won't. But remember, this is just exercises. I'm just doing the exercises. But I doubt that they are going to go into that topic. But we will here. It's not that difficult. We just have to be a little bit careful. We just have to reason a little delicately. Okay, so to that end, it would be nice if we could just kind of get one of those, those nice little if and only if liners that we've been seeing. That would be nice, very elegant, to just kind of this, if and only if that, if and only if that. But this is sort of tricky enough that we're actually going to have to split up this if and only if. So remember, to prove these if and only if, take this as our statement P, and this is our statement Q. What we're going to need to show is P implies Q, and Q implies P. So we're going to need to show two conditionals. Sort of this one implies that one, and that one implies this one. Generally speaking, you don't want to scare off your audience a little, right at the beginning. So you try to start with maybe the easiest conditional, even if it contradicts with the order of the statements here, and then move to the harder conditionals. So in our case, the easier statement to prove is going to be showing that given an injection, you can get a surjection. So to that end, let's get started. Suppose there exists, I'm going to try to avoid the quantifier notation as much as I can for this. I just think it's good to change it up and to kind of see, especially since a lot of this is not going to be, we're not going to have too many like equations or anything like that. This is going to there's going to be a lot of reading things out. So I think that using, there exists and for all kind of blend a little bit better with the format that we're going to have for this proof. Sometimes I think it's better to use the quantifier notation. Other times I think it's better to just kind of write stuff out. In this case, I think it's going to be better to write stuff out. So let's suppose that there exists a function, and instead of saying just a function, we'll call it an injection, because it's not just a function. We're going to assume this thing and prove that there's an surjection. So we're going to assume that there exists an injection. We'll call it F, going from A to B. Okay? So we're starting out, we're supposing that this is true. Let's suppose there's an injection from A to B. It follows then that F inverse is a function, right? Because F inverse is more generally, it's a mapping, right? It doesn't have to be a function. You can get the inverse mapping because sometimes, for example, f of x equals x squared. I mean, there is an inverse, it's just not an inverse function, right? If I have, f of x equals x squared, the f inverse of that, what if I plug in f inverse of 4? What is it going to be? 2 or negative 2, right? The inverse mapping will map to both. You get both, you get a set object out of it, right? But in this case, since it's an injection, we know that that's not going to happen. Whenever we have a b and b, there's going to be exactly one a that corresponds to it. Okay, so f inverse is a function. Then we can define a function g going from b to a, right? So this is going to be the setup then for our surjective function by, so here how do we define g? Well, what we're going to do is we're going to say g of b, so g has to take elements from b and give me back elements from a. And it's going to be defined piecewise. We're going to say g of b is just f inverse of a, sorry, f inverse of b, my mistake, whenever b belongs to basically the range of a. The range of a by f, right? Sorry, not the range of a, the range of f, my mistake. You could say the image of a by f, right? So basically this is whenever I find b in the range, right, then I'm just going to do f inverse b. Otherwise, I'm just going to pick a star. Now clearly, well, let me put this down. A star where a star is just an element of a. So let me make a little quick comment here. Should I maybe have said, okay, pick an element, since a is non-empty, let's pick an element a star from a and now define it this way? Sure, I think it actually might have been better to kind of go through that and actually establish that a star is just some arbitrary element that we chose, and we can do that because a is non-empty, but this isn't too big a sin. We're not too guilty here. I mean, this is acceptable. I mean, we're just saying a star is some element or some arbitrary element. Like I said, if you want to clarify, you can sort of up above here say, okay, let a star be some element of a, or since a is non-empty, we can pick a star and a. We can do something like that. But it's not that important, and we kind of get the idea across here. Okay, so now that we've done this, we have our function g. So we started off with an injective function, an injection, f, and we ended up with this function g that came out of it. But that's not enough. Right? What we want to do is we want to show that g isn't just some function. G is a surjection. So how are we going to do that? Well, remember, if something's a surjection, right, you need to show that for every element that's an image, well, I guess that's not true. What you need to show is that the codomain is equal to the range, basically, right? That for every element in the codomain, there must exist some element in the domain that corresponds to it, right? That's what it would mean for it to be a surjection. So to that end, what is g? G goes from b to a. So what we need to show is that for every element in a, there's some b that's getting mapped to that element by g. So how can we show that? So let a be some element of a. What I want to show is that a is the image of some b by g. So there exists a, well, actually, yeah, I don't want to, I already said I was going to stick to there exists, so let me write it out. So there exists a unique b and b such that a is f inverse of b, right? But then look at our function g. G says, hey, if you're getting mapped by some element in a, then you're just going to be f inverse of b. So A is equal to g of b. And that establishes the proof then, right? Because now I found that A really is the image of some b by g, right? So pick an A and A, I can find you a b that gets mapped to that A by g right here. And there we go. So let me just kind of graphically show you what we did in some sense, what happened here. The idea was basically we started off like, let's say this is A, our set A, and this is our set B, right? And let's just say this part of A, oh, sorry, my mistake. Let's say A got mapped into, say, this part of B, right? So all of A mapped injectively to that part of B, right? Well, what's going to happen, what we basically did was, okay, if f goes in this direction, then I can flip the direction here and go f inverse, right? But I'm missing all this, so I don't have a function on B, right? The domain wouldn't have been B, it just would have been on the range, right? So all we really did was for this portion out here, that wasn't part of the range of f, we just sent that to some arbitrary element in A. We just said, okay, for all this other stuff that we didn't actually have in the range, we're just going to send it to some arbitrarily chosen A in A. And now we have our function g, which is a surjection, right? Because we knew that we already used all of A, so all the extra stuff, we can just send it to some arbitrary thing. That's basically the whole proof technique here. OK, so I can reuse some board space here since we used up quite a bit of it. I'm going to erase this really quickly. And now we're going to do the trickier one. OK, so what we've shown is that when you have an injection, you can get a surjection. Now what we need to show is that when you have a surjection, you can get an injection. So to that end, let's suppose there exists some function which is a surjection g going from B to A. Now, I want to keep this same notation g here. Instead of putting f, right, we're starting with a function. This g doesn't necessarily have anything to do with our previous function g. I mean, they're not the same at all. It's just previously we've already sort of, g was associated with this motion from B to A, right? That movement was associated with g, so I don't want to disrupt that and make it confusing for ourselves. So I'm just going to keep g. G is some function from B to A, but that doesn't mean that g is related to the previous function. It's just some totally new function, g, it's going from B to A, and it's a surjection. What I want to show is that I can find some function which is an injection going the opposite direction from A to B. And how are we going to do this? OK, so since g is a surjection from B to A, we let x equal to this set of all g inverse of A's, which are subsets of B, where A is an element of A. So this is where we're taking our our first steps into something maybe slightly. We need to just be careful and let's see what we're saying, okay? Because you might be saying, wait, what are we doing? Why are we naming? What is this x? Let's take a look at it. So x is a set. What's inside of x? I mean, what is it? A set that looks like 1, 2, 3? Is it a set that looks like all real numbers? I mean, what is this set x? OK, this set x is a set of sets. It's a set of sets. So don't be confused by this notation here, g inverse A. Remember what I said before. There's a reason why I said this. Whenever you see g inverse, don't immediately think function. That's why I took the time to say f inverse was a function last time. Because generally speaking, whenever you see this, you don't want to immediately think, oh, it's the inverse function. Generally, you first start with thinking it's an inverse mapping. And that's important here because that's what this is. This is an inverse mapping. It's actually not a function. This is going to be a set. G inverse of A is going to be a subset of B. The reason being is, you might have, so if here's A and here's B, right? So what we have is a surjection from B to A. So maybe this is B1, this is B2, and this is B3, right? And over here we have A1 and A2, and maybe B1 goes to A1, and B2 goes to A2, and B3 goes to A1. So this is a surjection. Notice that every element in A here has a preimage. I mean, something is getting mapped to every element in A. There's no element in A here which is sort of being left out, right? But I can't see how these two both go to A. So if I look at the preimage the inverse mapping, right? What am I going to get for this A1? G inverse of A1. It's going to be a set with two elements in it, B1 and B3, because there's two things here, right? So it's not necessarily going to be the case that this is just some element. No, it's going to possibly be a collection of elements. So what this X is basically all of these backwards, right? Just go backwards, that's all it is. And then take the collection of all the things that you get when you go backwards, right? So for this A1, it would be the set B1, B3. For this A2, it'd be the set B2. So that would be that would be X. X would be for the first element. G inverse of A1 would be the set B1, B3. And when I plugged in A2, I'd get the singleton, the set B2. So it would just be the set B1, B3, comma, the set B2. Okay, that's what we're doing. We're taking a collection of sets with this X. Since G was a surjection, what can we say? Well, like I said before, it's a surjection, so it's not like we're going to be missing any A's, right? They're all going to be there in the image. So it follows that G inverse of A is not empty for all A and A, right? Because it's a surjection, it means we're not missing any of the elements in A, right? Everything in A, something's getting mapped to, right? For every element in A, I can definitely find something that's getting mapped there. So for every element in A, this G inverse, I can definitely find some B that's getting mapped to this A, which means that the G inverse is not going to be empty. So for every single A, I can be sure that there's not going to be some empty set in this collection. Why do I care? Because that's the condition that we need for the axiom of choice. So by the axiom of choice, it follows there exists this function h going from my collection X into B such that, this is my shorthand for such that h of G inverse of A is an element of G inverse of A. Now this is just the direct statement, really. What I'm writing down here is basically by definition of what the axiom of choice is. So I want to pause this for just a second. We're going to sort of stop the proof for a moment. We're going to sort of pause it, and we're going to look at what this axiom of choice is really quickly. I don't want to get too much into detail with it. It's an interesting topic because this is actually something that, there's some dispute about. Most of the time when you think of mathematics, you think everything is 1 + 1 = 2. This is certain. Everything's, a solution means that you know the answer. But believe it or not, there are things in mathematics where you can have an opinion, so to speak. Right? And the axiom of choice is sort of the quintessential example of this. I'm not really going to go into the disputes. I'm just going to say that some people reject the axiom of choice, though I don't think many. I mean, I personally don't know any. And then most people are sort of ambivalent. Like, if you want to try to work without it, try to work without it. If you want to work with it, you can work with it. I think most people, just to make their life easier and the concerns are not really relevant to them, they just accept it when they need it. Okay, so the axiom of choice, here's the statement of the axiom of choice. I'll try to... So the axiom of choice is going to say for any collection of sets, here's what's going to happen. You're going to have that if for all items in your collection such that that item is not the empty set, let me rephrase that. If it is the case that all the items in your collections are not the empty set, then it follows that there exists a function f so that for every item in your collection, the function of that item belongs to that item. Now that sounds like gobbledygook. That sounds like total gobble. What are you saying? Let me just simplify what this is basically saying. It's saying, okay, let's suppose we have some collection of sets, right? So let's say I have a set, and inside that set I have maybe the set, set with 1, 2, the set with 3, 4, the set with 5, 6, and so on and so forth. I just have a collection of sets. If it is the case that none of those sets are empty, so I have a collection of sets, none of which are empty, then here's what I can say. I can find a function f so that what this function does is it chooses elements from the sets in X, right? So let's say I have my collection of sets X, right? So here's my first y is a set. Here's my first set y, y1, y2, y3. What f is going to do is it's going to say, okay, give me y1, right? So f is taking y1. It's going to say, okay, y1 is a set. So I'm going to pick some element out of the set. Let's go to the next set, y2. I'm going to pick some element out of that set. I'm going to pick, and it's just picking elements. F is also known as a choice function, hence the name axiom of choice. It's basically just saying if I give you a collection of non-empty sets, you can pick elements out of those non-empty sets. Now, you actually don't need it in sort of non-general cases, like if you have finite sets and things like that, it's not necessary. But we don't have that assumption here, so we are going to need the axiom of choice. Okay, and notice that with this said, I sort of chose X to be X here. X is my collection. We established that none of its elements are empty, and so this H is really just my choice function. I'm just saying H is just some element in the set G inverse A, right? Which, remember, are just elements of B. It's composed of elements of B. It's a set of elements of B. Okay, now this doesn't quite work, though. The issue is you might be thinking, oh, now we found our injection. Not quite, because they're pretty explicit here about saying that it has to go from A to B, and that's not the case here. My choice function is going from a collection of sets, which that's not A. But that can be easily fixed. So we can define this function now f going from A to B by, and now we're not going to do anything fancy. There's nothing really fancy left to do here. It's going to be pretty straightforward. How am I going to define A? Well, it's sort of the only thing I can do. In some sense, when you're in issues like, how do I define something? It's up to me to define it. Sometimes it just helps. We'll grab onto something. What's the only thing I can grab onto? This is H, right? So f of, remember, it has to go from A to B, f of A, and it should give me back an element of B. Well, that's just going to be H of G inverse of A, right? First off, this I can plug in every A, right? Because this was defined for every A, so I can plug that in, G inverse. And this is a function. It's well defined because I'm picking one element. That's what the axiom of choice says. It's just some f of y, your choice function, h of y, is just some element in y. So h of G inverse of A is just some element of G inverse of A, which is an element of B. So f of A is just some single element of B. So f is a function. Now what we have to show is that this function f is an injection. To show that f is an injection, let f of A1 equal f of A2. So remember, this is kind of how you set up proofs that some function is an injection. You take two possibly different preimages and assume that their image by f is equal. What you want to show is that by assuming that their image is equal, the preimages must be equal. A1 must be equal. From here, my job is now to conclude that A1 equals A2. And how do I do that? Since g is a function, it follows A1 equals A2. And now if you put this back with our first proof, we've completed the proof of this entire theorem. I erased the original one going one direction, so I have a little more board space, and I have this. Let me kind of give you the visual schematic of what's going on here. Okay, so here I have some function A. Here I have some set A and some set B, right? And what I've established is that there's a surjection from B to A. Right, so this thing is going like this. Right, we have something like this. And this direction is going, this is G, right here. Right? G is taking elements from B into A, and I'm getting all the elements from A. I'm hitting all elements from A. Now, what we want to show is that there's some way of reversing this in some sense. And here's basically the idea. It's actually, this might seem a little convoluted, but the basic idea is actually really simple. Because all that's actually happening is this. Okay, G was going this way. How do I go back the other way and make sure that I get an injection? Here's what I do. Let's start with A1. Well, there was only one element that it was in its preimage, right? So if you look at G, the preimage of A1, I guess by G, was B1, right? So if I'm taking my function f, there's only one thing it can be. It could be B1. So f of A1 is B1. And I've got an injection so far, right? So far. Now let's look at A2. Now here's the issue. First off, I need it to be a function, right? So this can't be happening. And I need it to be an injection. So what I want to do is, this is where sort of the choice function comes in. This is why we needed this choice function. What it's going to do is say, OK, well, there's two here. Just pick one. Well, let's say I pick this one right here, right? And then that one, I don't care about it anymore, right? So f is going to take A2 to B2. Remember, I don't need a surjection. If nothing gets mapped to B3, so be it. It doesn't matter. All I need is an injection, right? And the reason why it's an injection, I know, is because G was a function to begin with. So we could have done a sort of contrapositive or contradiction, something to sort of clarify this. But if you don't have to, you tend to, the general advice is not to. Sort of what they'll tell you is off on the side of your paper, convince yourself. But this is not wrong. This is a function, so A1 equals A2. The reason why if you need more clarification in this, you could sort of try something like, OK, well, let's assume that that's not the case, right? OK, so then let's suppose I have an A1 and an A2 that are getting mapped to the same element by f, right? Oh, but that can't be the case, because if you remember, G was the function that was going from B to A, and G was a function. It's a surjection, so it's a function. So that would have meant that B was getting mapped by G to two different values, A1 and A2, which we know is not the case. We know that didn't happen. So that couldn't be the case, so it must have been the case then that A1 must have equal to A2 if their images were equal. OK? So like I said, that one was, again, a little trickier just because we had to use that axiom of choice, which wasn't actually covered, I think, in the text, at least not sufficient to actually deploy it here. You might have done something like assume that it was countable, so that you could write stuff like x1, x2, x3, or even more. You could have done something like, let's assume that these sets are finite, right? Which is basically like an application of the pigeonhole principle, sort of in some sense here. that's something that you could have done. Like I said, it's sort of, I think the idea of this problem was just to approach it at sort of your level of understanding of the chapter. So if this is like a brand new sort of thing for you, proving things in math, it might be better to go with whatever way you felt was more comfortable. But this is sort of the general way of doing it. All right, I hope it helped. I'll see you in the next video.